survey, and then we're going to talk about how we get high performance with traditional canvas and also with hardware acceleration. So when I talk about high performance, what I'm really talking about is making sure that the application or game runs smoothly with the highest possible frame rates. And I believe in lazy programming. So what I really mean is high performance with minimal effort, like the effort I used to translate these slides, as you can see. In fact, that's the last bit of translated text for quite a while. So what we're really talking about is responsiveness. We want to make sure that when the user is interacting with our application, that the entire device feels like it's very, very responsive to their touch. That's the most important thing we can get. So there are all sorts of rendering options in Android. And I'm going to cover this in this talk, mostly because it was in the abstract. And I realized looking at the abstract that I had about a 5-minute talk. So we'll spend the first 5 minutes covering the abstract, and then we'll start doing useful stuff. So there's Canvas, and there's OpenGLES, and there's RenderScript. I think there's the RenderScript guide. And we also have the NDK thrown in here. And in the NDK, we have OpenGLES, and we have this thing called native window, which is a quick, nice pixelized version. And what's cool about all of this is that we have options. But the question is, which one do we use? And it really depends on your needs. OpenGLES is fast because you get very close to the GPU hardware. You know, it has the highest quality, but the problem is, as a developer, it also doesn't shield you very much from the hardware. You really have to understand how it works. Android devices have different GPUs as well. So it also means that you have to kind of know a little bit about what's out there in the world of Android. But it's very rich, and it's very good for fast games. Now, if you miss having pointers, no matter, you might want to use RenderScript. You bet you thought I was going to say NDK there, but no, it's actually, so RenderScript is actually really cool because it gives you access to pointers, it gives you access to a whole structure for doing fast 3D graphics across different CPU types. So what ends up happening is your application actually, your RenderScript application, gets built and gets translated on the fly into machine code and actually cached, so it'll even run faster the next time you run it. And this works whether your final target device is something like Google TV or one of the Android tablets. And in the future, it's going to come to even more platforms. So today, it's only available on Honeycomb. But going forward, this is the future of Android high-performance graphics. The ability to target multiple devices with multiple CPU architectures with a single binary that runs very, very fast. It also does some very cool stuff. It gives you immediate support for taking advantage of parallelization in your code. So it actually has a loop that automatically helps you, if you build with its structure, divide your application into parallelized threads that can be run on a graphics processing unit when we have support for GPU in the future, for general purpose GPUs in the future, as well as today having the ability to automatically scale your task across multiple CPUs, which is what it does in Honeycomb today. Also in the future, we're going to have multiple neon and vector processors. So we're actually going to be able to use this to help write code automatically to help your application take advantage of hardware floating point, neon code, multiple CPUs. So in other words, it's kind of complicated. But this is the future. Probably not the present. The present is probably more OpenGL plus NDK. And the reason why is, of course, the NDK was added as of Android 1.6, and so all the devices have it, while only the 3.0 and above devices have RenderScript. And this is cool because it allows you to get closest to the hardware. You can do whatever you want. It's a little bit more challenging to tie this into the dollar code that runs the rest of Android. But this is very standardized. And this is really useful for people who are trying to bring code over from other platforms, and also people who are really used to programming in C++. Now, as a show of hands. How many people out there program in C++? How many people out there prefer programming in C++ as their favorite language? See, not everybody loves Java. It's amazing. Or how many people prefer to program in JavaScript? Okay, I think it's kind of crappy. So that's good. You can program in JavaScript too, and that's actually one of the things that NDK allows you to do is use whatever interpreter you want. But yes, there's a lot of code written for other languages other than Java, and we want you to be able to run them on Android, so we created the NDK. Now, that's part of it. We also have native window. And native window is cool. We added it in Gingerbread. And this allows you to render graphics straight into a framework. So this is really useful for people who want to take old games that were written for PCs years ago and bring them to Android. You can actually do this with native window. It's very, very fast. It's the fastest way to do this, but it only works in the NDK, and it works only in Gingerbread and above. So this is kind of still the future of doing certain tasks, but it's very, very useful for those tasks, especially for things like emulators. So now we've covered two things. Let's talk about Canvas. Now, people would argue to me that Canvas is really not high-performance graphics, but it is the most feature-rich and easiest way to draw to the screen. You know, we support text rendering, bitmap drawing, scaling, rotation, skew, and perspective. But the question is, how do we draw to the canvas in a high-performance way? And there's a very non-obvious solution. Okay, well, it's really not that non-obvious. We want to draw the smallest number of pixels. And we want to draw each pixel only once. So both of these things are actually really important. So I'm going to go through a little bit of general guidelines on how we do that. So one, we want to invalidate only the parts of the screen that are changing. We want to set the background threads to background. Okay, this has nothing to do with drawing pixels. This is just how to keep things responsive. We want to avoid memory allocations in our draw calls because that'll cause the virtual machine to have to do a garbage collection, and you'll see the app go like this. And there's nothing worse when you're scrolling with your hand and it jitters. So we want to try to make sure that nothing actually allocates memory while we're doing scrolling. And we also want to use shallow view hierarchies. You can create very complicated things, and Android does pretty well with it up to a point, but it has to do a lot of additional calculations. List view. Okay, almost everything in Android uses lists, whether it be a list of contacts or I don't know, everything uses lists. Even grids are really just specialized lists. So these are all things that there's tons of data out there and knowledge out there. But this is just a review. Again, we use view holders that keeps us from allocating. We don't use managed queries because they happen in the foreground. We want to do things like set an opaque background where it makes sense. And we don't want to use wrap content on list views because that means that it has to calculate a whole bunch of additional calculations to lay out our lists. Again, this is all review. Is this review to most people? How many people know all this? Just by a show of hands? Okay, so that's good. So this is important stuff to know. There's actually two great talks that have been done about list view. One of them was a talk done in 2008 at Google I/O by Randy, where he talked about how to do responsive applications. I definitely recommend looking that one up. The other one that's really, really good is there's actually a talk that he did only on list view last year for the 2010 GDD. They're both really, really good. Canvas. So this is kind of interesting. You can actually make Canvas run really, really fast because Canvas has actually always been composited with the main screen using OpenGL. And so if you want, you can actually draw to the canvas using something we call the surface holder. Surface view. And this gives you this access to this object called a surface you can change the size of. And then what it does, when it actually composites that to the screen using something that's inside of code we call surface slinger, it actually then will automatically scale it in hardware. So sometimes this is the answer to the biggest problem we have in performance games. If you want to do a game in Canvas, for example, you can actually do this, and it gets rid of most of your fill rate problems with a little loss of quality. The other thing we can do is cache complicated drawings, and we can rescale images. Now, there was a general call. You listened to that session in 2008. He actually says rescale all of the images. Today, I would say don't bother scaling them up. Because if you scale an image up, it takes more memory. And we're always, don't have enough memory. And secondly, it actually makes things slower sometimes. If you're doing hardware rendering, it'll actually be slower to scale up in software and have a larger image that it has to put on the screen in many cases than it is to just put the smaller image and let the hardware do it for you. But if you do want to do it, that's how easy it is to create a scaled bitmap. All right, so this is all the review. And again, there are some really, really good lectures out there on this, but I wanted to cover it because this is useful throughout all of Android. Now, in Android, we have always done the vast majority of the rendering in software. And what this means is that, yes, we actually use OpenGL to composite everything when everything's all done rendering. But when you render text, we actually had the CPU go and manually copy the bytes over one at a time. And so that's kind of slow. So when Honeycomb came out, we had this idea. Let's try putting the UI on the GPU. Give us the best advantage of having Canvas and OpenGL ES. And the reason we did this, because admittedly, devices are getting faster. If you played with the original G1, the original G1 had a fairly small screen. But now, we have this size screen. So you look at it, the G1 actually had a fill rate that was pretty good for the size of the screen. And we went up to the Droid. We actually almost got an equivalent amount of fill rate for the size screen for the number of pixels we had. So the Droid felt about as fast as the G1, even though it had far more pixels to fill. And then with Nexus 1 and Nexus S, it got even faster. But all of a sudden, you see zoom. The pixel count goes way up. And the speed of our fill rate actually went down. So the realization was that there was no possible way this was going to work. This tablet experience was going to be truly terrible if we didn't come up with a solution that allowed us to draw more pixels with this even smaller fill rate that we had on the zoom. So with software rendering, it looks like this. Each view is drawn, and that draws to a canvas. The canvas then is responsible for rasterizing it, and it goes to the display. But when we add in hardware, we actually, after the canvas is drawn, it goes to this OpenGL render, which goes to the GPU. And this is actually a very high level of what happens. So let's take a list view. So these are all bitmaps and text on the list view. You can actually see at the top of it and the bottom, there's actually this effect, which is a fade effect, which you can see drawn with additional polygons. And each one of these are turned into quads, into two triangles. And we create a texture. We rasterize that texture for the different text, which is actually done using a shader. And then we have textures for each one of the icons in this list. And that's how we draw a list in hardware acceleration. And it even gets better with 9 patches. Because this is one 9 patch. And 9 patches are specified, of course, as a part that is scaled and a part that's fixed size. And so all we have to do is change the geometry underneath, and it'll automatically scale that 9 patch for us in real time. So it's pretty cool. Now the question is then, how do we draw high-quality lines? Well, as you can see, high-quality lines are tricky because the hardware doesn't support them automatically. So we still draw them into a quad, and we put them into a texture. So this is how the system works. Basically, the shaders are generated at one time based upon the effects that you have turned on and what you're drawing. So basically, in this case, we're drawing, this is a vertex shader that actually goes and draws text with a gradient fill. And actually, this is pretty simple. You really don't see much going on with the gradient. That's much more useful in terms of the fragment shader. So this actually gets created on the fly. In fact, we have millions of combinations of shaders that are automatically created on the fly as you apply different effects to your graphics. So the question is, what do you have to do to enable this in your application, to enable all of this cool technology that our engineers spent months working on? Does anyone know here what do you have to do to turn this on? Show of hands? Okay, well, you have to do this, okay? That's all it takes to actually enable acceleration in your app. And you're going to want to do this because the next generation of Android phones is going to require it for decent performance, because they're going up to higher and higher densities on the screen with higher resolution graphics. And if you don't turn this on, your application is going to run very, very slowly. Now, of course, the question that I get asked is, why don't we just turn it on by default? Well, because compatibility is ultimately more important than performance. We want to make sure that your application continues to work. And there are a few things that don't quite work or don't quite work the same way. The good news is, this is at the application level, but you can actually control it at all sorts of different levels. You can actually make a single activity hardware accelerated, or even a single window hardware accelerated. And there's even a way to turn hardware acceleration off at the view level. So the way we do it at the application level is pretty straightforward. For a lot of applications, all you have to do is put hardware accelerator equals true, and that's it, you're done. You do some testing, it works, it's great, it runs really fast, but maybe it doesn't work for a single activity, so you turn it off. On the Windows side, we actually can set flags. So you actually have to do this from code, and you can turn it off and on at the individual window. And then finally, this is really, really cool. We've had layers in Android for a very, very long time, which actually buffer drawn graphics to a secondary part of memory. But we've actually exposed them inside of Android 3.0. So you can actually say, I want to set a layer type. So in this case, that particular view will be drawn in software, and it will be drawn compatibly. You can also create GPU-aware code. So you can actually, if you're writing custom views, you might actually want to know, should I draw this way or not if I'm using hardware acceleration? So that's another thing you could do inside of your code. So the question again is, why don't we turn it on for everyone? Well, of course, the 2D APIs, it turns out, in Android is really, really awesome. Like, you can do a lot of stuff with canvases. The problem is it's really, really hard to accelerate a lot of these operations. It's very hard to do them on the GPU at all. So what we have are some missing features and some limited features. Now that being said, all of the standard views and drawables will work. Here are the caveats. These are things that will not work. Certain kinds of clipping, a few kinds of drawing, and some of these paints. So these ones won't work at all. Now, how many of you out there have actually used one of these, by a show of hands? Has anyone used one of these painting methods? I think probably the one for me that I've used is draw text on path. And I've used draw position text once, but admittedly not that often. But you can still use them, you just have to use them in a software layer, or render them to a bitmap. Another thing we have are some limitations. So we have a few things like drawing lines didn't support anti-aliasing until Android 3.2. Colors are ignored from drawing bitmap meshes. This stuff is all pretty well documented, but it's definitely worth knowing that there are some limitations. Some of these just don't make any sense. Like, why would you set filtering on? Filtering is free with hardware accelerations. There's no reason to turn it off. Same with dithering, it's just ignored. And then also, if you play with Canvas, there's this actually very, very cool feature called shaders that is built into the canvas, which are these 2D software shaders that you can do things like, again, use to render gradients and do very, very complicated operations. And basically, you just can't have two shaders of the same type, as well as a shader that contains another shader. These are pretty reasonable limitations. It's pretty rare. Has anyone here used the shaders, by the way, in their app? Has anyone used something that's going to break? Okay, that's good. But the shaders are really cool. I definitely recommend looking at them. They're kind of awesome. But again, you can always use a software layer. So let's talk a little bit about what the new drawing model looks like. It's still an immediate mode drawing model, but it uses a special kind of caching. So the old model looks like this. Basically, you have your view root, and that ends up calling a group, which calls down into individual views. And those views are asked to render themselves. But here's what it looks like. That view gets invalidated. It tells its parent, hey, I've been invalidated. It then tells the view root, hey, that part of me has been invalidated. And then it calls and it draws the portion of that group, and it draws the portion of that group. So that means there's a lot of Java code that's being called each time this is happening. But the logic actually remains the same for each one of the parents. This is a really expensive way of drawing the screen. So what we've done is we've created a display list. So to redraw a view, we simply reissue its display list. And this display list actually is entirely done in native code. There's no Java. It looks like this. So this actually will be the display list that redraws a button. So basically, we get rid of all of the interpreted code. And we also have a few other optimizations thrown in at the same time. Like in the old model, you would actually end up redrawing things that didn't have to be redrawn. Like, you were invalidating the top object, but redrawing the bottom object completely. So what's cool about this is we invalidate view B, it marks that display list as being dirty. And then when it redraws, all it has to do is rebuild that display list, and then only rebuild the one that's actually been changed. So it's much, much faster. And let's examine this as an example of what happens when we enable Wi-Fi in the settings of the Zoom. We're going to tap that and look to see what happens in both models. So this is what happens in the old drawing model. The checkbox gets hit, we turn on Wi-Fi, there are Wi-Fi selector panel, all of this drawing. Lots and lots of code. And in the new model, this is what happens. So only one tiny piece of Java gets executed, and the rest of it is entirely done in native code from those display lists. The only difference in this is an important thing, is that we only now draw a view. We draw a view when that view is invalidated. So one of the most common mistakes that keeps things from being compatible is by code that assumes that we will actually redraw automatically when a view on top of it gets invalidated. That no longer happens. You actually have to tell things to invalidate if you want them to update, even if they're on different layers below the main screen. So it's an important difference. Because in the old model, invalidating a view meant redrawing intersecting views. And this was not actually intentional. This was just a side effect of the way it worked. Now with the new model, we invalidate, it only draws the actual children that are being redrawn. So you see that side display list doesn't get redrawn. Now we briefly mentioned layers, and they're useful for compatibility, but they're actually useful for much, much more. They can actually be used to control compositing. So what we can actually do here is call the display list with draw and add a layer onto it. And that layer has its own paint property, which is pretty cool. So only when the layer is drawn on the screen, it's only a texture, and it can pretty much be done on the GPU. So the default layer disables buffering. This is good because it saves a lot of memory. The software one, of course, renders the view into a bitmap. It's very good for compatibility because it forces software rendering. But you should only use it if it's really necessary because it does cost memory. And then finally, this view gets rendered into a frame buffer object using OpenGL hardware acceleration. It's very, very fast. It only costs GPU memory, and it's optimized for blending. So here's an example. Hardware layers render view into a hardware texture. And This allows for this kind of performance. So when we're drawing a list view that gets drawn into a hardware layer, and we have to, let's say, do an animation on it, we're going to move it around. Okay, it's not changing the value of the list, we're simply transforming the list in some way. You can see it takes almost no time in the hardware layer. It's still pretty fast with the display list, and it's pretty slow in software. So we can really use this for visual effects. Because remember, we get to apply a paint to it. So we can actually do this. This is an example here of just applying a simple effect with a color filter to a paint. And that's all we have to do on that hardware layer type, or on the software one. And boom, we now have everything drawn in gray, all on that layer. To do this before, you had to explicitly set the properties of each one of those objects. So let's talk about compatibility. That's probably one of the most important things. I talk about software layers a lot. Again, they take a little bit of memory. They're not good in every situation. They'll slow things down for software layers, but they give you that level of compatibility. And of course, finally, as I said, animation. The most important reason to use layers are to handle animation. Things like opacity and size and origin, all of these properties here are really useful for dealing with layers. Because again, it draws it into a bitmap, and then the GPU can just start spinning and scaling and rotating and pivot and change the alpha value as it does the compositing step. So all of the really cool, fast animations that we see in Honeycomb are made possible by these layers-friendly properties. So again, we set rotation, it invalidates the view group, it gets marked dirty. And that's what happens. It's very simple. The display list gets drawn, rotated, redrawn, and restored. So this allows us to animate a complex view very efficiently. So there is a problem here, though. Let's say you're using a list view. And you want it to transition and do this really cool flying effect. But for the most part, it's just a waste of memory to have that hardware layer on. So all we have to do is change the layer type on the fly. So we're about to go and rotate this and make it fly around and do something cool. So okay, let's set the layer type to hardware. And then when the animation's done, we'll just set it back to having no layer. And that allows us, again, to have really high performance while keeping our memory count down. So a couple of tips to kind of leave you here with. One is we have to be very careful of using set alpha in general on our layers. Because if you put set alpha on a layer and you're not using hardware layers, it actually costs an enormous amount of fill rate. So set alpha is a really good example of when you want to use a hardware layer. Because it actually allows you to, it does it all in the compositing step all at once. Reusing rendering objects are always important. It follows our general practice of not allocating very much. It also if you reuse rendering objects, it actually forces this whole additional new shader creation. Don't modify bitmaps often, and don't modify paths often. So one of the key things that's changed in hardware accelerated rendering on Android has to do with paths. So basically, in the past, you draw a line. That's pretty fast. It draws another line. That's pretty fast. And you can keep drawing those lines at very high speed. If you turn on hardware rendering, every single time you draw a line, it has to go and generate a texture. And then for fast compositing. So that's a perfect example of where it wouldn't make any sense to turn on hardware acceleration. And there's lots of cases like that. But the key thing is that what's happening really in the background is the system is trying to optimize around compositing, rather than optimize around things like actually performance of geometry. So it's sort of an interesting side effect of the way this all works. So that is actually the presentation. So I wanted to leave you with a couple things. One is that definitely look at Google Dev Lab app. That's my Google Plus and my Twitter. Also, just some really good stuff on Roman, who wrote the hardware accelerated rendering system, and also Chet, who actually put together the animation system for Honeycomb. And they have a lot of really cool stuff on this. And I'm ready to take questions now. So please.